This is the second part of our discussion on the root test. In the previous part, we defined and discussed what is lim sup of any sequence of real numbers. In fact, we discussed it for positive sequence of real numbers. Now, let's recall ourselves how did we define limit supremum or lim sup of a given sequence of positive real numbers. So it is denoted as lim sup n approaches to infinity Tn, and it is equal to L if L is the smallest real number with the following property, that for any epsilon there are at most finitely many terms in the sequence that are larger than L plus epsilon. So let's say this is the real line and this L is basically the lim sup of this sequence. If we take any epsilon, okay, so any arbitrary epsilon, so it could be as small as possible or as large as possible. So let's say if this is the epsilon, then this number is L plus epsilon, and the condition is there should always be finitely many terms on the other side of L plus epsilon or bigger than L plus epsilon. So there are always finitely many terms over here, and it should happen, or it should satisfy this condition for every epsilon, and also this number L should be the smallest one satisfying this condition. If this happens, then we say that L is basically the lim sup of this sequence of positive real numbers. Now let's define root test, and over here you can see that we are using this lim sup, and we are calculating this lim sup for this sequence of positive real numbers in which we are taking the nth root of the modulus of the terms, the moduli of the terms of this this series. Okay, and if this is equal to L, then the series absolutely converges if L is less than 1, and it diverges if L is greater than 1. And similar to the case of ratio test, this root test doesn't say anything when L is equal to 1. So in other words, when L is equal to 1, the test is inconclusive, or we can say that the test fails, and we need to find some other criteria, some other way for checking the convergence or divergence of this complex series. Okay, now before going to the proof of this test, the root test, let's apply this root test in this very simple situation where the terms of the series are 1 plus iota over n raised to power n. Now observe that of course when we have for example many tests at our hand, and there are many tools for checking the convergence or divergence, then one important thing is what test should we apply. So for example over here, if we want to compare for example root test and ratio test, and we want to see whether should we apply root test or ratio test in this case, then this power n guides us that if we apply for example a root test in this case, then it will be extremely simple because the nth root will cancel this n and we will get a very simple situation. Now over here, what is the nth term? So the nth term is going to be equal to 1 plus iota over 2 raised to power n. And what do we need to calculate? We need to calculate the lim sup n approaches to infinity of the moduli of this terms of the sequence and the nth root of them. Now let's apply this definition of xi n in this case. So lim sup, so we want to calculate 1 plus iota divided by 2 raised to power n modulus 1 over n power. Now of course this is going to be equal to limit n approaches to infinity, so 1 plus iota divided by 2 raised to power n multiplied by 1 over n, and this n will cancel out this n, and what do we get? So we get 1 plus iota over 2. Now 1 plus iota over 2 does not involve any n, so in other words it is just a constant sequence. Okay, so this is going to be equal to 1 by 2 plus iota 1 by 2 modulus, and in this case we can calculate the modulus to be equal to 1 by 4 plus 1 by 4, and this is going to be equal to, okay, So this is going to be equal to 2 by 4 or 1 by 2 or 1 by square root 2. Now in this case we can see that L is equal to 1 over square root 2, and 1 over square root 2 is basically equal to 0.707, and which is less than 1. So this implies that the given series converges. So that's how simple it is in this case to apply this root test to check the convergence or divergence of this series, and this series in fact converges by using the root test. Now let's have a look at the proof of this root test. Of course there are two cases. So the first case is when L is less than 1, and the second case is when L is bigger than 1. So let's begin with the first case when L is less than 1. Okay, what is our assumption? So our assumption is the lim sup of this sequence where the terms are basically, okay, so zeta n mod and then 1 over n, and is equal to L. Okay, so this is the lim sup, and of course L is less than 1. And what do we want to show? We want to show that this series converges absolutely in this case. Okay, now if L is less than 1, okay, so let's say this is the real line and this is our L and this is 1, and over here L is less than 1, then between L and 1 there are infinitely many real numbers. Let R be one such number such that R lies between L and 1. Using properties of real number, it is a very simple situation that of course there will be some R that lies between L and 1. Now by definition of lim sup, there are only finitely many terms of the sequence greater than R. Now why this is the case? Okay. Now let's say this is L, this is R, this is 1, and the claim over here is there are only finitely many terms over here. Okay, so there are finitely many terms. So this is the claim, and this claim is true by definition of the lim sup, because we know that L is the lim sup. Okay, so this is the lim sup and approaches to infinity of this sequence. So L is the lim sup of this sequence. Okay, and by definition of lim sup, for every epsilon, so in this case let's take our epsilon such that L plus epsilon is this number R. So for every epsilon there are only finitely many terms bigger than L plus epsilon, and L is the lim sup, so that's why there are always going to be finitely many terms bigger than L plus epsilon. And if we choose epsilon such that L plus epsilon is equal to R, then this statement is true. So by definition of the lim sup, there are only finitely many terms, or in other words we can say that there are infinitely many terms over here. So infinite terms over here. And when we say infinite terms, in other words we can say that after some integer, all of the terms are going to lie in this interval. Okay, so precisely speaking, all of the terms after some capital N, all of the terms are going to be less than R. Okay, and which implies that the modulus of zeta n is less than R raised to power n whenever n is bigger than or equal to capital N. So that's our observation so far. Now let's use this observation to check the convergence in this case. Now let's recall ourselves that the geometric series is convergent if the modulus of z is strictly less than 1, and in this case this series converges because R is less than 1. Now remember, R is somewhere over there. R is a number between L and 1, and which is strictly less than 1. So that's why this geometric series converges. And also using this thing and comparison test, we can say that this series converges after n plus 1. Okay, so we are just using the comparison test, and we are comparing our given series with this series of real numbers. Okay, and in this case this condition is satisfied, so that's why this series is convergent. And since adding or subtracting finitely many terms in the series does not affect the convergence or divergence of the series. So that's why we have this series to be convergent. And of course, these are the absolute values of the series, and using the result that absolute convergence implies convergence, hence this series converges, and this implies that the series n is equal to 0 to infinity zeta n converge. So now let's move on to the second case. So the second case is when the lim sup is equal to L and L is bigger than 1. What do we want to show? We want to show that this series diverges. Now if L is some number which is bigger than 1, let's say this is 1 and this is L, then once again using the properties of real numbers, there are infinitely many numbers between 1 and L. So let's say R is just one such number that lies between 1 and L. Okay. Now once again using the definition of lim sup, there exists capital N such that all of the terms are bigger than R, okay, for n greater than or equal to capital N. And of course we can see that why this is true, because L is some number bigger than 1 and R is number over here, and the claim is all of the terms of this sequence are going to be bigger than R, okay, so over here after this capital N. And it makes sense because the statement is for epsilon, okay, if we take an epsilon, then after this epsilon there are going to be finitely many terms over here, and over here all of these infinite terms will be here. So that's why this statement makes sense. Now this implies, by taking the powers of both sides, the modulus of zeta n should be greater than, strictly greater than r raised to power n, and this implies if and of course r is bigger than 1, okay, so remember r is bigger than 1, so this implies that the limit of this sequence cannot be equal to 0, because all of the terms for infinitely many n, so or after this capital N, all of the terms are bigger than r raised to power n, and r is greater than 1, so this r raised to power n is going to be a number which is much bigger than 1, so that's why it cannot converge to the origin. And this implies that the limit of zeta n cannot be equal to 0, and this implies according to the necessary condition, if the series of complex number converges, then the limit of the terms should be equal to 0, and since in this case the limit is not equal to 0, so very easily this series diverges. Now in this discussion we discussed what is root test using the definition of lim sup that we discussed in our previous discussions, and we also applied this thing in a very simple situation, and we also discussed its proof. Now this is one very powerful tool for checking the convergence of a given series of complex numbers.